Hi, Assalamualaikum. Welcome back to my channel Physics from 5 KSSM. Today we continue Chapter 7 Quantum Physics on Topic 7.1 Quantum Theory of Light. In this video, I will discuss 5 learning standards. The first one, explain the initiation of the quantum theory. The second one, describe quantum of energy. The third one, explain wave-particle duality. The fourth one, explain concept of photon. And the fifth one, solve problems using photon energy formula E equals to hf. And also power, P equals to nhf. Let's get started. In Form 4, we have studied about electromagnetic waves. In the topic, you are introduced to electromagnetic spectrum. The electromagnetic spectrum is a continuous spectrum. What is the meaning of continuous? Continuous spectrum means there's no gap between the series of electromagnetic waves, gamma rays, X-rays, ultraviolet, visible light, infrared, microwave, and radio waves. The spectrum of electromagnetic waves are arranged according to frequency and wavelength. As we discussed before, electromagnetic waves travel at speed of light. By using the formula V equals to F lambda, electromagnetic waves travel at speed of light C equals to 3 times 10 to the power 8 meter per second in vacuum. When speed is constant, the relationship between frequency and wavelength is F is inversely proportional to wavelength of waves. If we look at for gamma rays, the distance between two peaks or crests is lambda. You can see it is shorter compared to the wavelength of radio waves. So we can see that from gamma rays to radio wave, wavelength increases. When lambda increases, frequency decreases. Same thing when we discuss about frequency. From radio waves to gamma rays, frequency increases and wavelength decreases. For the visible light, which the range of electromagnetic wave that human can see, is the color that produced by dispersion of white light. When white light disperses, when passed through the water droplets, for example, it will produce 7 colors: red, orange, yellow, green, blue, indigo, and violet. These 7 colors, we call it visible light, and they are also arranged according to the wavelength and frequency. From red to violet, wavelength decreases, frequency increases. The electromagnetic waves that we discussed in electromagnetic wave spectrum just now can be absorbed or emitted, and it is known as electromagnetic radiation. When we talk about electromagnetic radiation, does all objects emit electromagnetic radiation? Or does human or another object emit electromagnetic radiation? Let's discuss about objects with different temperature. Cold objects emit wave with low frequencies, such as radio wave or microwave, which is low frequency and longer wavelength. For the hot object, emit wave with higher frequency, such as visible light and ultraviolet radiation. Hotter objects emit most of radiation at shorter wavelengths, hence they will appear to be bluer. as what we discussed about the spectrum of color just now, the visible light, red, orange, yellow, green, blue, indigo, and violet. From red to violet, lambda decreases. So the shorter wavelength will appear bluer or near to violet color. Cooler objects emit most of the radiation at longer wavelengths. Hence, they will appear to be redder. As you can see, red color is longer wavelength. Furthermore, at any wavelength, a hotter object radiates more or is more luminous than the cooler one. As you can see, we compare red color and yellow, so yellow is more luminous than red color. In order to observe the radiation that emits by an object, sometimes you need to use a special camera, because if the color is out of the visible light range, human cannot see. We need to use a special camera like infrared camera so that we can observe the color. Okay, when we talk about radiation that emitted or absorbed by an object, there is an object that considered as a perfect absorber or perfect emitter of radiation. We call it black body. What is meant by this black body? A black body is an idealized body that is able to absorb all electromagnetic radiation that falls on it. A black body can also emit thermal radiation depending on its temperature. The radiation emitted forms a continuous spectrum and is unaffected by nature of the black body surface. Thus, an object emitting electromagnetic radiation, which is determined by its temperature, is known as a black body radiator. Why is black body? Why we call it black body? Because those bodies that absorb incident visible light will seem black to the human eye. Means, if the object absorbs all the light and does not reflect it at all, it will appear black. As example, the leaf appear green because the green absorbs the other 6 colors or the visible light and just reflected green color. Thus, we can see the green color. Example, we can hardly characterize our sun, which is indeed almost a black body within a very wide band of electromagnetic radiation wavelength, as a black physical object in optics. It is namely bright white sunlight which represent the equilibrium black body radiation. Okay. Certain object at certain temperature, for the object which is low temperature, it will emit a range of radiation about infrared color that the human cannot see. And when the temperature increases, start to emit radiation. So you can see the color is more to red and yellow. Thermal radiation is electromagnetic radiation that includes visible light and radiation that cannot be seen by human eye, such as infrared radiation. As example of the bulb, at low voltage, small current, so you can see the filament give the color of about red color. When voltage is increased, it will become more yellowish color. So this one you can explain by using the spectrum of visible light as we discussed before. Red, orange, yellow, green, blue, indigo, and violet. The black body radiation cannot be explained by wave theory of radiation, same as the phenomena of photoelectric effect. The particular nature of electromagnetic radiation is discussed by Planck's quantum theory. The black body radiation also can be discussed when light rays enter the ear cavity, which the rays will undergo repeated reflection on the inner walls of the ear cavity. At each reflection, parts of the rays are absorbed by the inner walls of the ear until all the rays are absorbed. Thus, the ear cavity acts like a black body. It absorbs all the light rays that enters into the ear cavity. Let's look at more about black body radiation. As we know that black body is a perfect absorber and perfect emitter of radiation. When such a body is heated, it becomes red hot. In other words, it emits red-colored light. As the temperature is further increased, the color of radiation emitted changes from red to yellow to white and finally to purple as temperature becomes very high. This implies that wavelength of radiation emitted by black body decreases with increase in temperature. If you look at the graph, intensity against wavelength, temperature T1 is smaller than T2. You can see at temperature T1, all range of wavelength of radiation are emitted, but the highest intensity is at the peak value, which is called wavelength maximum. It's about the value of 1500. And then when the temperature increases to T2, the wavelength at the peak value or the wavelength maximum decreases to become less than 1000 nanometer. So from here we can see the higher the temperature of the object, the shorter the wavelength of radiation emitted. The color that can be seen is the wavelength which has the highest intensity, means the color with wavelength at the peak value shown by the graph. As temperature increases, you can see the maximum value of intensity, or we call it wavelength maximum, shifted to the left, showing that the highest intensity at the shortest wavelength. When the wavelength approaching to the wavelength of ultraviolet, we can see intensity of light suddenly drop, and it produces a narrower part of graph on the left side. So means a hot object will emit a very low intensity of ultraviolet. And this situation we call it UV catastrophe. And this part cannot be explained by classical theory and also wave theory, but then can be explained by quantum theory. Let's discuss more how the quantum physics theory able to explain this graph. According to classical theory, electrons vibrating at the same frequency should have same energy content. The vibration frequency of electrons also has no limits. However, experimental results involving black body radiation are inconsistent with classical physics theory. Based on the graph of radiation intensity against wavelength for black body radiation, the light intensity on the left side of the peak does not continue to increase with the increase of wave frequency as predicted by classical theory. If we look again at the graph, according to classical theory, when frequency of wave increases, the intensity of light increases. So that's against the shape of the graph that you can see, because at high frequency, suddenly the intensity of wave decreases. As you can see, the intensity of ultraviolet decreases, even though at high frequency. Thus, it is called UV catastrophe and become a challenge to classical theory, and then explained by quantum theory. Let's look at classical theory that's studied by Isaac Newton, Thomas Young, John Dalton, and J.J. Thomson. For Isaac Newton, the study about particle nature of light, it is unsuccessful in explaining the phenomenon of light refraction due to failure in comparing the speed of light in glass and air. For Thomas Young, carried out double-slit experiment, also unable to explain the radiation spectrum produced by black bodies. John Dalton atomic model, unable to explain the light spectrum produced by atoms. J.J. Thomson, discovery of electrons, unable to explain the line spectrum of light produced by atoms. For quantum theory, Max Planck introduced the concept of quantum, which is discrete energy. The electromagnetic wave emitted by black body is in discrete form, known as quantum of energy. He also produced the energy in each quantum is directly proportional to wave frequency. The intensity of radiation is low for high frequency wave, such as the UV. Albert Einstein introduced the photon concept. The photon energy is directly proportional to light wave frequency. Einstein's quantum theory of light was successful in explaining the characteristic of photoelectric effects that could not be explained by classical theory. Niels Bohr explained the production of line spectrum by hydrogen atoms. The electrons in an atom orbit around its nucleus on certain shells only. The transition of electrons from higher energy level shell to lower energy level shell emits photon. Louis de Broglie introduced the hypothesis of wave nature of particle. In 1924, Einstein and de Broglie then postulated the idea of wave-particle duality of light and all subatomic particle. So this one discuss about lighter particle like electrons. According to quantum of energy, the electromagnetic spectrum may be a continuous spectrum or a line spectrum. As we discussed before, electromagnetic wave is in continuous spectrum. For example, the dispersion of white light by prism produces a continuous spectrum consisting of 7 visible colors. This spectrum has wavelength range from 400 nanometer to 750 nanometer. The line spectrum produced by an excited atom is a series of colored lines with unique wavelengths and frequency. Each element produces spectrum with a series of its own distinctive lines. So you can see the line has its unique value of wavelength and frequency. Thus, this line spectrum can be used to identify elements. Let's say a hot black body emits radiation. When passed through a prism, dispersion produces continuous spectrum in form of visible light. Black body emits light at all wavelengths. So this one is continuous spectrum. When the hot black body emits radiation and then pass through cloud of cooler gas, what happens to electron? Electron will receive energy, and then when passed through a prism, we can see absorption of line spectrum. Atom in gas cloud absorb light of certain specific wavelengths, producing dark lines in the spectrum. And then the emission of line spectrum, atom in the gas cloud re-emit the absorbed light energy at the same wavelengths at which they absorb it. So you can see the first diagram showing absorption line spectrum. You can see the line which is black because the cloud of gas already absorbed the color. Okay, so the color is in form of line spectrum, and then re-emit the color, it also forms a line spectrum. Based on the line spectrum that produced, the frequency of color like violet, blue, green, yellow and orange, for example, can be determined. because each of the color line has a distinctive and unique wavelength. And then the energy quantum also can be determined. Quantum of energy is a discrete energy packet and not a continuous energy. As we know, if continuous, there is no gap between the spectrum. The energy depends on the frequency of wave. Thus, we can calculate the value of energy of photon. According to Max Planck and Albert Einstein quantum theory, light energy exists in the form of energy packet, known as a photon. Photons are light energy transferred in quantum of energy. Energy of wave is not transferred continuously as what discussed in wave theory. It is in form of packet or discrete, and we can count the number of photons emitted. The value or the number of photons can be calculated as 1, 2, 3, 4, and so on. It is a discrete value. So from here, we can say photons are light energy transferred in quantum of energy. And the photon energy is directly proportional to frequency of light. E directly proportional to F. Thus we get E equals to HF, where H is a constant known as Planck constant. The value is 6.63 times 10 to the power of negative 34 joule second. By using this formula, E equals to HF, energy of photon can be determined. Light is a type of electromagnetic wave. It also behaves as particle. Other types of waves in the electromagnetic spectrum can also behave as particle. That's all for today. I will continue to discuss on problem solving using formula of energy of photon E equals to HF, and also the concept of wave-particle duality. Thank you for watching.